Hello student, welcome to our lesson today. We are going to continue with capacitors and capacitance, but in here we are going to start by defining the capacitance, and later we are going to look at factors affecting capacitance. So capacitance is defined as the charge stored in a capacitor per unit voltage. You know that a capacitor is a device that stores charges. So in here we can say that capacitance C is equals to charge Q over voltage. That is mathematically. So we have C is equals to Q over V. From this formula, we can make V the subject of the formula as well as Q as the subject of the formula. So Q will be CV, and then if you want V, it will be Q over C. But now, let us move to the SI unit of a capacitance. Now, the SI unit that is used, if you look at this one, we can get it from here directly. That will be coulombs divided by voltage. But the coulombs per voltage is equivalent to farad. Therefore, the SI unit that we are going to use in our calculation is farad. We have the definition of farad as follows. A farad is a capacitance of a body if a charge of 1 coulomb raises its potential by 1 voltage. Then we move to multiples and sub-multiples of farad. We have 1 microfarad is equivalent to 10 to the power negative 6 farad. And this is the one that we are going to commonly use in our calculation. Then we have 1 nanofarad is equivalent to 10 to the power negative 9 farads. Then 1 picofarad is equivalent to 10 to the power negative 12 farads. After that, we can look at factors affecting the capacitance of a parallel plate capacitor. And for us to understand this concept, we need to describe an experiment. In this experiment, we have this as the apparatus. We have uncharged electroscope. We have 2 plates, P and Q. We have the studs that will help us to place these plates parallel, that is to stand upright. So, having these apparatus, we have the following as our procedures. Number 1, fix the plate on a support and place them to stand parallel and close to each other. You can be able to see how we have placed this plate. They are parallel to each other. The distance between them is D. Then we have P and Q, P and R. This one is the earthed, while this one is charged. So, charge plate P, this one, to a higher voltage and connect it to uncharged electroscope, then add the second plate R. Now, while keeping the area of overlap, this one, the area of overlap between P and R constant or the same, we are supposed to vary the distance or the distance of separation D. And this one is varied by either bringing closer R to P. And then you are supposed to observe the divergence of this leaf electroscope. Then from there, while keeping the distance of separation D constant, vary the area of overlap A by moving R sideways. You move your R sideways. You have this as your R. As you move it sideways, you will vary the area of overlap. Again, after doing that, you're supposed to note the new deflection. Then after that, while keeping the area A and the separation D constant, introduce a glass plate directly. Remember, before we introduce this one, there were air particles that were in between. Now we want to see if we change the dielectric, what will happen to the leaf divergence. And we have this as the observation. First of all, we are starting with the area of overlap of the plates A. So, increasing the area of overlap and keeping distance D constant, it makes the divergence of the leaf decrease. Note we are increasing the area of overlap and the divergence is decreasing. So what you're supposed to note is that the divergence of the leaf is the measure of the potential on the plate, which implies the greater the diffraction, the higher the potential. And we know that C is equals to Q over V. So from here we can say that C and V are inversely proportional. That is, the capacitance and the voltage are inversely proportional. And Q is the constant because now we are not changing the amount of charge. So it implies that the smaller the value of diffraction, that is V, the higher the capacitance. We have seen that they are inversely proportional. The smaller the voltage, the higher the capacitance. So the greater the deflection, the smaller the capacitance. So from here, we can say that because as we increase the area of overlap, as you can see, we increase the area of overlap, what is happening in the divergency is that we are decreasing, which implies that as we increase the area, the voltage is decreasing. And remember, the decrease is referring to, or the deflection is referring to the value of the potential difference. Thus, we can say that the capacitance is directly proportional to the area of overlap. In other words, C is directly proportional to A. Then we come to the distance of separation, D. When the distance of separation is increased, the divergence increases. Thus, we can say that the capacitance is inversely proportional to the separation of the plates. That is, C is inversely proportional to 1 to D. That is the distance of separation. Then after that, our last procedure, we are supposed to introduce a glass plate as our dielectric. And by so doing, it was observed that when the area of overlap and the distance of separation are kept constant and the dielectric is introduced, the divergence of the leaf decreases, which implies that the nature of dielectric also affects the capacitance of a capacitor. Because initially, before the introduction of the glass plate, the air particles were acting as the dielectric. By introducing, we see the change of the leaf divergence, which implies that we have 3 factors that affect the capacitance of a capacitor. 1 is the area of overlap, then number 2, the distance of separation, and number 3, the nature of dielectric. Then from there, from all that experiment, we can say that we have a factor that we call permittivity that is dependent on the medium that is being used as a dielectric. We have seen that a capacitance depends on the nature of a dielectric. You introduce a glass plate, this constant will change. You use a paper, this constant will change. So it means that we have a term, a constant that we call permittivity, that is having a letter epsilon of the insulating material. And this permittivity is a constant that is depending on the material media that is being used between the plates. So if the plates are in a vacuum, this constant that we are calling permittivity is denoted by epsilon naught, and its value is 8.85 times 10 to the power negative 12 farads per meter. Then we can have the expression of a capacitance. We have seen that C, that is the capacitance, is directly proportional to the area of overlap and inversely proportional to the distance of separation. So if we replace the sign of proportionality with an equal sign and a constant, then we get that C is equals to epsilon A over D, where now our epsilon is this constant that we are calling permittivity. We can make this permittivity the subject of the formula, and you will get that epsilon is equals to CD divided by A. If you divide the units, the capacitance is farads, the distance is m, that is meters, and the area is meter squared. So 1 meter will cancel with meter or for the distance. So that is how we are getting that the SI unit of permittivity is farads per meter. We move to an example. 2 plates of parallel plate capacitor are 1 millimeter apart, and each has an area of 6 square centimeter. Given that the potential difference between the plates is 90 volts, calculate the charge stored in the capacitor. We proceed as follows. We have the capacitance as epsilon A divided by D. So we substitute our values. We are given the epsilon because we are considering to be in a vacuum. We have that is the value. Then the area, you convert this into square meter. And then the separation distance, which is 1 millimeter, you convert it into meters. Now, when you key in all these values in your calculator, you find that the capacitance is 5.31 times 10 to the power negative 12 farads. But we know that Q is equals to CV. So our C is this value. Then we multiply by 90, which is our volts. We were given this one. When you multiply, you get that Q, the amount of charge, is 4.779 times 10 to the power negative 10 coulombs. After that, we have the assignment. This one is testing all what we have covered. So make sure that you revise, you revisit, discuss with your peers, and then come and attempt the assignment. So thank you, and let us meet in our next lesson.